Ready? Okay. Hey. First of all, are you voting the talks in Guidebook? No. How many of you are voting the talks on Guidebook? Okay. Okay, fine. Okay, the first talk of this afternoon is done by the release manager of Python 3.4, as has been a contributor of the Python language from the 90s, right?
No, yes, actually, yes.
Yeah, so here it is. All singing, all dancing, Python bytecode. Thank you.
Okay, so I'm going to go really fast because I've done this twice today and I ran out of time every time, so we may not have time for questions. But, so to introduce the talk, this talk is an intermediate talk and it's all about Python, specifically CPython. CPython is the implementation of Python that's in C, as opposed to the implementation of Python written in other languages, like Jython is written in Java and IronPython is written in C#. CPython is just the version of Python that's written in C, but that's what you get when you type Python at your local prompt. So I'm going to be talking about CPython because bytecode is specific to CPython. Specifically, I'll be talking about Python 3.3 because that's the current version, and I'm a core developer, and I like current versions of things. The talk will be 100% in Python. You don't have to understand any C to get out of this talk because there will be no C on the slides. This information is generally applicable to other versions of Python. It's most applicable to previous versions of 3, but then it's generally applicable to versions of 2 as well. PyPy has its own bytecode, which is very similar, but not exactly the same. And then IronPython and Jython, the purpose of those is to use their own local VM system bytecode. So the bytecode itself doesn't look anything similar, but the concepts involved are generally the same. So let's start at the top. What is bytecode? Bytecode I would describe as the instruction set for a virtual machine. Now, I seem to break out this analogy every time I talk. Python has a virtual machine, and this is one of those very few apt metaphors in computer science, in that it is both virtual and a machine. It is virtual in the sense that it doesn't really exist in the real world. It's just software. It's not a warm box that you can go over and kick. And it's a machine in that it has all the attributes of a real machine. And when we say a machine, we really mean computer here. So it has an instruction pointer, it has a stack, it has memory, it has registers, and it has an instruction set. The instruction set of a virtual machine we generally refer to as bytecode because each instruction is usually a single byte. So I would break CPython's virtual machine instruction set, its bytecodes, into rough 4 categories, and these are very rough. But there are opcodes to manipulate the stack. These are mainly loads and stores. There are flow control instructions. These allow you to manipulate the instruction pointer, and this is jumps. There are instructions to do arithmetic, like binary add. And then there is this catch-all category I call Pythonic, which has a lot of stuff in it. And this would include things like build a set, or build a tuple, or start a closure. These are all things that are very specific to Python. They're bytecodes, but they're not things that you would see in like an Intel instruction set or something like that. They're really there just to make the virtual machine's implementation a lot easier. So, when does Python use bytecode? The answer is all the time. Anytime that you're running Python code, you're running Python bytecode, because the first thing that Python does when it takes your code and wants to run it is it translates it into bytecode. Which means, actually, that anything you can express in Python, you can express in Python bytecode. So Python bytecode is actually a relatively powerful programming language. In fact, it's more powerful than Python. There are things you can do in Python bytecode you can't do in Python, such as you have a goto instruction. You can jump directly to any place you like. You can't do that in Python, and for good reason. So it's a little late to be asking this question, but why bother looking at bytecode at all? Why are you all here? I've been wondering that. I can come up with one very good reason, which is if you're going to be a core developer on Python. In order to understand how Python works, you have to understand bytecode because it's central to the implementation of Python. And I'm a slide ahead again. God, I did this last time too. I'm talking ahead a slide. I really should go back a slide and talk about why have bytecode in the first place. Why do you want to have bytecode? Why add this layer of complexity to an already complicated thing? It's actually to manage the complexity of the interpreter. This is a very standard technique. When you're writing an interpreter, basically everybody has a bytecode. PHP has a bytecode, although it's crazy. Ruby has a bytecode. And as I said, all the different implementations of Python, they all have their individual bytecodes. It's just a way of taking the incoming program and breaking it down into little pieces. So it's a divide and conquer strategy, just like any other approach to programming. So on to the slide where I thought I was, which is why study bytecode in the first place. And like I said, the only reason I can come up with is if you're going to be a core developer. Now, there are three reasons that people often talk about that they want to understand bytecode, and I don't really like any of those. There's one that is to understand what's really going on. And understand what's going on under the hood of Python, you need to understand bytecode. And this is theoretically intellectually satisfying, but my problem is, where do you stop? If you say, okay, to understand Python, you really need to understand bytecode. Okay, well, to understand bytecode, you really need to understand C. And to understand C, you need to understand assembly language. And understand assembly language, you need to understand the microcode of the CPU you're running on. And underneath that is digital logic and transistors. And under that is physics and electricity. And under that is special relativity and quantum mechanics. And I'm going to assure you, ladies and gentlemen, that you don't need to understand quantum mechanics and you can still have a full, rich life programming in Python. Now, a second reason that people cite is that they want to write hand-tuned bytecode. And again, I don't like this just because it's theoretically fragile. Python makes no promises that it's not going to change the bytecode from one version to another. That said, it really doesn't change that much. But I think if you're trying to wring out a couple extra cycles here and there, you're probably better off just going back to your algorithms and trying to make your program generally faster and keeping it in Python. And the final reason that people cite is, and this is actually a relatively good reason, the bytecode is the granularity at which the GIL will be swapped out and you'll change threads. This is not literally true because you can also drop the GIL inside of C code, but if you're just running Python instructions, then the Python interpreter can switch in between instructions. So consider just like a simple line like A equals B. There's two opcode instructions there. There's the load of B and the store of A, and the GIL could switch in between. So in order to really understand what could happen in a sort of a multi-threaded Python program, you do kind of have to understand what bytecode and how granular Python breaks down when it's running. So to talk about bytecode, I really need to have a sample program. This is my sample function. It's called gunk. It's really terrible. It doesn't do anything interesting. I just want to draw your attention to it because I'm going to be breaking it down over the course of the presentation, and I'd like you to remember a little bit about it. So it takes three parameters, a positional or keyword parameter called A, which takes a default of 1. There's star args, which is a variable arguments array. It's going to contain any additional positional arguments, and that's always going to be a list. And a keyword only argument called B, which takes a default of 3. Then we call print args. We create a local variable called C and set it to none. And then we return this really stupid tuple, which contains A plus B and the value of C. So let's go straight into disassembling this. Python has built in a disassembler. It's called dis. It's the dis module, and inside of that is a function called dis. And here's the output of dis.dis run on gunk. So it's kind of readable. Let me go through the columns first. This first column, this is the line number offset that the bytecode appeared on. So the first 4 bytecodes were all on the first line. The second column is the bytecode offset that the bytecode appears at. So it starts at 0, and the next one's at 3, and the next one's at 6. I did say that bytecode is made out of bytes, so why are these 3 and 6 and 9 and 10? What's going on is that a bytecode can be optionally followed by what's called the op-arg, which is an optional 16-bit unsigned number. And if you have one of those, then you eat the next 2 bytes out of the bytecode stream. What you do is you take the first one, you take the second one, shift it left by 8, and you OR those together, and that's your 16-bit number. Most of these opcodes are taking an op-arg argument, which we're going to see in the 4th column. So that's why load global, the next one is 3, and then 6. Pop-top does not take an op-arg, so it goes from 9 to 10. This column, of course, is the name of the bytecode itself, load global, load fast, call function. This column is the op-arg that I mentioned before, and as you saw, pop-top doesn't have an op-arg. Most of the rest of them do. It's just pop-top, binary add, and return value that don't take one. And then this last column is dis giving you kind of a hint as to what the op-arg represents. So load global 0, what that's actually loading is a global named print. Load fast 2, that's loading a local variable called args. but it's not telling you how it arrived at that information. And in general, I find the output of dis kind of disappointing because I take a kind of a holistic approach to Python bytecode. In order to understand Python bytecode, you really need to understand not just the environment it runs in and not just the bytecode, but all the data and metadata associated with the program. Consider for a moment a modern, just a C program that you write. So the C program, you compile it and you produce assembly language, right? But there's a lot of data associated with that. There's the static variables, there's the strings. If it's a modern program running on a windowing system, it might have dialog boxes and fonts and bitmaps and pointers all stuck in this one executable program. And the assembly language doesn't make sense outside of the context of all that other stuff. So I think that you need to understand the data and metadata associated with bytecode in order to really understand it, and this doesn't show you any of it. You look at this, you can't tell the difference between A, B, args, and C. C is a local variable, A is positional or keyword, args is this list thing, and you can't tell the difference just staring at that. So I find dis not up to the task. So I wrote my own disassembler and assembler, which we're going to talk about in a couple of slides. So like I said, I'm going to talk about the whole picture. I'm going to talk about the opcodes themselves. I'm going to talk about the VM, which is the environment that these things run in. And I'm going to talk about the data and metadata associated with a runnable object, a callable object in Python. So let's start with the opcodes. There are 101 opcodes inside of Python 3.3. And bytecode is it's stored in a byte string. You can think of it as a list of integers. Each one of the integers is going to be less than 255. So an individual opcode, we call opcode or bytecode kind of interchangeably. We always call that op for some reason. So an op is just a single byte, and it represents a particular bytecode. And then if we take the op arg, like I mentioned before, we look at the next 2 bytes in the bytecode stream, and we take the second one and shift it left 8, and we OR them together. Now, how do you know whether a particular op takes an op arg? Well, that's actually pretty easy. There's this value. It's stuck in dis. It's available to you Python programmers. It's called dis.haveArgument. It's currently the value 90. And the way it works is, if the op is less than 90, wow. I am boring the president of the PSF. If the op is less than 90, then it does not take an op arg. And if it is equal to or greater than 90, then it does take an op arg. So therefore, the size of the total op is either 1 or 3, depending on whether or not it is less than have argument. So let's talk about the VM. There are really 3 pieces of live data inside the VM that you care about if you're going to be running opcodes. There's the instruction pointer, which you can manipulate through jump instructions. There is the stack pointer and the stack itself, which you can manipulate through load and store instructions. And there are what they call the fast locals, which are loaded and stored specifically through load fast and store fast. Those are the things that deal with fast locals. Now, fast locals, this is an optimization that Guido added a long time ago. This is essentially a Python list, and arguments and local variables are stored in this list in specific offsets. So loaded fast 0 will be the first argument if the function took any arguments, or would be the first local variable if it didn't. I'm going to talk about those in depth in a minute. But I just wanted to show you the stack. In case you've never seen a stack, I'm going to have a really crappy LibreOffice diagram for you. So all the load instructions, there are 6 of them, and I'll show you those in a minute. They all copy a value from somewhere out in memory onto the stack. So here is what it kind of looks like theoretically. Let's say that this is the CPython stack. The CPython stack can store any arbitrary Python object. So I have here a tuple. On top of that, I have the callable object, which happens to be called print. And we're going to push 3 on top of that. So boom, look at that. That was exciting. The symmetric option is called store, and there are 5 store instructions, and they take the value off the top of the stack and store it, tuck it away somewhere in memory. Slightly less uninteresting would be something like binary add, which is going to take 2 values off the top of the stack, let's say 12 and 17, pull them off, call dunder add on them, or dunder r add, depending on whatever it has to do, and whatever the result is, it's going to push back onto the top of the stack. So, like I intimated a minute ago, there are 6 different places that you can load variables from. Load globals, the load and store global. So I'm going to just have load here, but there are equivalent store instructions for 5 of the 6. So globals and built-ins you access through load global. And all of these load and store instructions take an oparg. In the case of load global, that's an index into an array that's associated with a function called names. So load global 0 is going to be the 0th entry into the names array, and whatever that thing is. The names array is actually a tuple of strings. And whatever that string is, you're going to look up that global or built-in. Store global does the same thing, or the symmetric operation. Fast locals, as I mentioned before, that's load fast and store fast. Those are going to load and store into that fast locals array, and the oparg is just the index into the array. Locals, these are what I call slow locals. These are, Python originally just had locals, it didn't have fast locals. And Guido realized that these were too slow for general use. So that's why he added the fast locals relatively early in the life of Python. But the slow locals are still used. These are loaded and stored using what's called load name and store name. And these are used for classes, for modules, and if you're running eval. Consts are loaded and stored using load const. There is no store const, otherwise they'd be very poor consts. And the oparg is just an index into another different tuple called the const tuple. Object attributes are loaded and stored using load adder and store adder. You have to push the object, and then the oparg is an index into the names array, and that's the attribute you're going to load and store. And finally, we have what are called cell variables, which are loaded and stored using load deref and store deref. And I'm going to talk about those in length in a minute, but I'll just say for now that, once again, the oparg is an index into the names array. So what are free variables and cell variables? I didn't understand that until I wrote this talk, and it took me quite a while to figure out exactly what it is. But consider the function foo. Function foo has two local variables, a and b, and then it has a local nested function called bar. And inside of bar, we have a non-local variable called b. So a is a local variable. We all understand that. B is a specific kind of local variable called a cell variable. A cell variable is a local variable which is referred to in a nested function. And conversely, B inside of bar is a free variable. A free variable, this is a term from compilers. It means a variable defined in another basic block or something like that. But in the context of Python, a free variable is a local variable that was defined in an outer function that we are referring to. So I'm not going to talk all that much about free and cell variables, in part because I don't understand them that well. But free and local variables are relevant to nested functions and, by extension, to closures. So finally, we're going to talk about all the data and metadata associated with a function, and there's an awful lot of it. So if you just take a look at the type of gunk, that is of class function, and you can find it in the types module under function type. If you look inside of gunk with dir, you're going to see a lot of stuff. I've made bold and large the particular fields that are relevant specifically to a callable object. Gunk is a callable, of course. I'm going to go over all of these again in a lot of detail, so you don't have to memorize them just yet. I just wanted to sort of show you the high-level view. But there's one I want to draw your attention to, which is dunder code there. Dunder code on a callable object is a code object of type. It's in the types module as types code, or excuse me, code type. A code object is, again, a very important component of a callable object. And if we look inside of the code object for gunk, we again see a whole bunch of stuff. All the stuff that's specific to a code object starts with CO underscore. Now this kind of begs the question, or at least to me, actually that's the wrong phrase. It begs the question is not what that is. But that gives rise to the question, why bother having both? If you have a function object, and every function object has a code object, why not just get rid of the code object and fold it all into the function object? So the first thing I want to point out about this is that the function object contains mutable or dynamically calculated data. The code object contains only static, immutable data. So that's one helpful thing to keep in mind, the difference between the two. And I thought this led directly to what I thought was the reason, which was that code objects are marshallable and function objects are not marshallable. Now what is marshal? Marshal is a binary serialization format that's built into Python. It's kind of like pickle, but it's a lot more restrictive. It's a lot faster, it's a lot smaller, but you don't want to use it because it changes violently from Python version to Python version. It's really only intended for one thing, and that one thing is it's the format of a .pyc file. So a PYC file contains the following things. It contains 12 bytes at the top, which are a 4-byte magic number which reflects the version of Python it was compiled with, a 4-byte date and timestamp of the py file when it last changed, and a 4-byte size of the py file as of the time it was compiled, which, by the way, that field is new in Python 3.3. After these 12 bytes is a single marshaled code object. So you have to be able to marshal the thing in order to store it. I thought that's why you had this separation between a function object and a code object. I asked Guido about this, and he said, no, that's actually not it. This separation existed before we even had marshal or PYC files. And the reason for it is nested functions. Oh, that's an example, by the way, just of some data that's on a function object that is not marshalable. The closure, the defaults, the KW defaults, and the globals. And again, I'm going to go over all of them in a minute. I don't know my own slides. But the reason, nested functions, this is why Guido added the separation between the function object and the code object in the first place. Remember our function foo on the previous slide where we had a nested function bar. Every time you run function foo, it's going to create a new function object representing bar. And if I had to populate everything that was in it every time, that'd be kind of slow. And so it's a lot faster to take all the stuff that's static and unchanging and stick it in one object and then just refer to that object every time that you bind the new function. So it's a little faster and saves a little bit of space. So finally, the moment you've all been waiting for, this is the actual bytecode of gunk. You ready? There it is. It's a byte string. It is one of the least legible things on the planet. Slightly less illegible is if you print it out as integers. So I can tell you, for instance, just if you want to try and read it yourself, every number here that's larger than 10 is going to be an opcode. So anything that you see that's less than 10 is part of an oparg. This 116, that's load global. So that's load global 00, that's load global 0. The second one is load fast, 124. 131 is call function. The last one, 83, that's return value. But again, this isn't terribly readable. However, I can write a disassembler for Python bytecode in a single slide. And here it is. Now, there are some values that I needed to pull out of the dis module, which is a disassembler, so this is a pointless exercise, but it's instructive. So here we go. In the disassembler, I print out def and then the name of the function and the colon, so it's nice and pretty. I pull out the bytecode string. I initialize my instruction pointer, and then I loop until I hit the end of the program. For each operation, I pull out the opcode, and then if it's less than half argument, then I don't have an oparg, and I increment by 1. If it is equal to or greater than half argument, then I pull out the oparg, I reassemble it properly, and I increment by 3. And I print out the result. And I look up the op inside of dis.opname, which is a map of opcodes to strings that represent those opcodes, so that it's nice and readable. And the result of running disassemble on itself is this: load fast 0, load chatter 0, on and on and on it goes. And again, binary add doesn't take an oparg, neither does poptop. It goes on for quite a while. If you want to see the disassembly for gunk, I'll show you that in a minute. Now, let's go back to the fields that are the metadata associated with a code object and a function object. These are the two fields that deal with arguments specifically. CO_argcount, that's the number of positional or keyword arguments. We only had one, called A. And there's CO_KW only argcount. They only had one, that was B. You can see their names in the, that's right, we have CO_n locals first. N locals is the total number of local variables. And I'll remind you that local variables are all arguments and all local variables. So gunk had 4, A, B, args, and C. And you can see those names in the var names array. Args was in the middle, you remember when I declared it, but when Python issues the bytecode, it actually reorders them. So the order of things in N locals and in var names is always all keyword or positional parameters, followed by all keyword only parameters, followed by star args if you have one, followed by star KW args, star KW args if you have one, followed by all local variables. And then those variables are in the order they were declared. Default values, as I alluded to a minute ago, if the function has any defaults for positional or keyword parameters, they'll go in here. This is a tuple, and the way this works is if you had 5 positional parameters and 3 of them had defaults, then this tuple would have 3 things in it, and you're just supposed to shift it over by the number of things that didn't have defaults. If you have keyword-only parameters that take defaults, there's a dict called KW defaults, and this is a lot easier to read. It's just a mapping of the name of the parameter to its value. More globals and const tables. This is relevant to load global and load const. This is the names array that I mentioned that a lot of the load and store keywords use. Gunk only has 2 globals that it refers to. Actually, it only refers to 1. It refers to print. This none that appears here, that's actually junk left over from tokenization. I asked somebody about it. They're like, yeah, we've been too lazy to clean up for, I don't know, a decade. CO_const is the const table I alluded to that load const uses. And this gunk only ever referred to 1 constant value, and that was none. So that's load const 0. Line numbers. Python doesn't use line numbers for anything except tracebacks and debugging and disassembly. And so it's very heavily optimized for size rather than speed. So there are 2 fields, CO_first line node, that's the first line number in the source file where this function appeared. And then there is this really hairy thing called LNO tab. It's another binary, it's a byte string. And again, slightly more readable if you printed out the individual integers. Everybody hates dealing with it. It's essentially pairs of bytes. That is the delta of the bytecode followed by the delta of the line number. And they have to come in pairs, and there are some rules on you can't have zeros in certain ways, and if you have a number greater than 255, you have to do something else. It's a headache, and hopefully you can live your life never dealing with LNO tab directly. So we're almost done with the metadata. I think I have 2 more slides, this one and the next. Globals, this is a reference to the dict of the module where the function was defined. So a callable object actually carries around a reference to its own globals dict everywhere it goes, which is why you can call a function from anywhere and it can still find its own globals. The dunder module is the name of the module where it was defined. Dunder code.co_filename is the name of the file name where it was defined. Code.coname is the name of the function. And CO_flags, this is this bit field flags array, which is probably the least documented part of bytecode and callable functions. I'm going to talk about it a little bit in a minute. But for now, let's just accept that it is number 71. Finally, the CO_stack size. Python pre-calculates how deep the stack will ever go when we're running the current function so that it can pre-allocate the stack in advance. And actually, what I thought was kind of interesting is it allocates 1 object for everything all at once. It's called a frame object. And that contains like the instruction pointer and the stack pointer and all sorts of things. And the end of the frame object is the locals array, followed immediately by the stack, all allocated in 1 big shot. This whole thing is called f_locals plus, very excitingly. Finally, we really are just about done with all of the metadata. We have annotations. Gunk didn't have any, so this is an empty dict, but this would be a mapping of name of a parameter to its Python 3 type annotation. Closure. If gunk was a closure, this would be I think it's a tuple of free variable references, but gunk is not a closure, so it is empty. It's just none. And then we have cell vars and free vars. Gunk is neither a nested function nor does it have a function nesting inside it, so these are both empty tuples. So one of the things I think is really interesting about Python is that everything's a callable, and that includes modules. So a module, you can think of it as a lot of code, right? Well, code lives in callable objects. So modules are therefore callable objects. So what do you get if you disassemble a module? Well, it's pretty boring, actually. It's just like a function that takes no parameters and then always ends in load const none followed by return value. All of the code that represents the module is going to be in that ... And literally, you can pull out if you create a module object, at some point when you load a module, you're going to have a function that looks exactly like this. And by the way, in Python, if you don't explicitly return something from a function, then it automatically returns none. So this little load const none return value, we're going to see that a couple of times. Anyway, a module is a callable that doesn't have any fast locals. All of its local variables, it uses slow locals, and those become the attributes of the module using load name and store name. So by the same token, the modules are callable. Classes are also callable. This is slightly more complicated. A class function actually takes a parameter, which we call dunder locals. And I'm going to sort of go this from the bottom up because it increases complexity that way. So at the bottom, we have the standard load const none return value. Classes return none when they run. Then we have all the code that represents the guts of the class. Then we have this load name store name, load const store name. That's setting up the dunder module and dunder qual name attributes of the class. And then at the top, we have this load fast store locals. What is that? Well, load fast 0, of course, is going to load the locals parameter and push it on the stack. And then store locals, what does that do? Well, this has to do with something that's new in Python 3. It's called dunder prepare. It used to be kind of viewed as a problem, quote unquote, that when you created a class dict was always a real dict. And some people wanted to have their own funny dict-like object there. So this is the mechanism by which the dict-like object is inserted into the class before we actually run any of the code. So that's what the class object looks like, but there's actually a little bit more work you have to do when you actually run that object. So this is also going to show us making a function a little bit too. This is, again, awfully complicated, and I probably should have had a sample making function earlier. But essentially, this make function thing right there, that takes a const code object and turns it into a callable function object. So let's start from the top and work our way down. Load build class, this is another one of those awfully Pythonic bytecode operations. All that does is push something onto the stack. It's a callable object called build class. On top of that, we push the code object that represents the class, the body of the class function, and then the name of the class, because that's terribly important. We always want to know the name of the thing. And we call make function 0. Now, make function 0, that pops the top two things off the stack, and then it looks at this number 0. This number 0 here, the op arg here represents three things. It's the number of annotations, the values for the annotations. It's the number of of default values for positional parameters and default values for keyword-only parameters. And those would all be pushed on the stack at this point. Since class object doesn't take any of those, this number is 0. The result of make function is going to push a real callable object that represents the body of the class on the stack. And then we have load const again and call function 2. Call function, the op arg represents how many positional parameters there are and keyword-only parameters. Positional is the bottom 8 bits, so this number 2, this means we have 2 positional parameters and no keyword parameters. So call function is going to pop two things off the stack. The first thing is going to be load const class name, that's the name of the class. The next thing is going to be output of make function, that's the callable object that represents the body of the class. And then it's going to pop the third thing off the stack, which is _build class, which is the top thing we pushed there. And it's going to call that function. So it's going to call build class on the callable object and the name, and that does all the magic whirligig stuff that makes the actual class happen, in case you were ever wondering. Now this is probably a little bit more interesting. I'm going to create a function in Python by hand, just using straight Python code. It only takes me 4 lines, but this is the least readable thing in all of my slides. So there's a code object that I'm creating by passing in all the right stuff in all the right places to the code type constructor, including the byte string. You can see the bytes, that's the middle line there. And then I just bind that to a function by passing in a globals dict, and I get a resulting function. This add thing on the left, that is a callable object. If I call that, I pass in 2 parameters, it adds them together, and the result is printed to the screen. That's prints 5. Now this is terrible and unreadable. So I'm going to do it again over 3 slides and make it much more readable this time. First, I need inspect and dis as well as types, so that I can pull out a bunch of symbolic constants to make it readable. The rest of the page here is just to make the bytecode string. So dis op map get, that's going to give me, that's going to allow me to translate strings into opcodes. So op load fast, that's going to turn into the appropriate number, 126 or whatever it is, followed by the op arg, 0, 0. And then so we're load fast 0, 0, that's going to load fast 0, that's going to be the first argument. Load fast 1, 0, that's going to be load fast 1, that's going to load the second argument. Binary add, that's going to take the top 2 things off the stack, add them together, push the result, and then return value is going to return the result, push it back onto the stack. That's all we needed to make add work. This page is all the arguments that we're going to pass into the code constructor. We have 2 arguments. We don't have any keyword-only arguments. We don't have any local variables, so those are both 0. The total number of locals is the number of local variables, the number of positional arguments, the number of keyword-only arguments. If we had star args, we'd add 1. If we had star star kw args, we would also add 1. N locals is the total number of local variables we allocate, and in this case it's 2. Max stack depth, this is also 2. This is the total depth of the stack we will ever achieve. This is 2 because I pushed 2 things for binary add. Flags, this is that bit field that I mentioned before that's really badly documented. In order to make Python happy, you should pass in these 3 things. Basically, every time you're creating a classic function in Python. So what do these mean? Well, co_new locals means that it uses the fast locals array. basically every callable object since about 1992 has had CO new locals defined on it. Maybe we could get rid of it. We forgot to do it in Python 3. CO underscore optimized actually means that the namespace is optimized, not the code for the function is optimized. And what this means is that it's actually going to use the fast locals array for local variables. There are 4 places that don't use the locals array for local variables. That would be classes, modules, eval, and any function that uses import star. Because if you say import star, we don't know what things could be local variables at that point, so you have to use the names, load name and store name. And del attr? Yeah, that's probably true as well. Del, and then the name of a local variable. Interesting point. I'll add that maybe. Or maybe I'll leave other people in the dark. CO underscore no free, that's a little hint of the Python interpreter saying this function doesn't have any free variables or cell variables, and so it can skip a bunch of calculations it otherwise would perform. It's just an optimization to actually run without it. So the function doesn't have any constants, any names, any free vars or cell vars, so those are all the empty tuple. It does have 2 local variables, a and b, which are parameters. The file name is standard in, the name is add, the first line number is 1, and the LNO tab is blank because I'm a jerk and I don't want you to be able to debug this function. And finally, we create the code object, we pass in all of those parameters in the right spots, and then the rest of it is exactly the same as the first slide, where we bind it to the function object, we get add, and we pass it in, and it works. But it's really painful to do all of that. So I wrote my own assembler in Python 3. It's called Maynard. I will remind you that Maynard was the keeper of the holy hand grenade, the finest disassembler known to man or beast. And I want to show you what Maynard looks like when it's disassembling gunk. So I think this is a lot more readable than dis output. You can see arg, that's a positional or keyword argument. Its name is a, its value is, its default is 1. Keyword only argument, that's b, its default value is 3. Arg's value, that's star args, that's going to be named args. We have 2 global declared in advance, print and none. Again, this none is worthless, but I'm disassembling gunk, so I have to show it to you. Const none, that's the only thing declared in the const array. Local C, that's our only local variable. And then we're off to the races. Load global print, load fast args, and you can tell exactly what all this stuff means. Call function 1, that's not so good. It's actually a little better in the modern Maynard. These are just old slides. So what if you wanted to assemble a class with Maynard and you wanted to see what the code looked like for a class object? Eventually, Maynard will just do that all by itself. You'll be able to disassemble a module and it'll show you everything recursively inside. But I'm not quite up to recursive disassembly yet. So there's a little trick you can do. Let's say that you have a class H and you have the entire contents of the class defined there and you want to disassemble that. Just throw it inside of a function and disassemble the function. When you look at the output of foo, you're going to see the code object as a static thing, this const code object. And again, this is not reversible. Maynard can't round trip code quite yet, or at least not complicated code. But anyway, this is a big clue here. It's like, oh look, const index 1 code object H. So the code object for the class you defined H is in the const array in slot 1. And so you can just pull that straight out of the foo code object and disassemble it, and that'll show you the disassembly for class H, which is how I produced some of the slides earlier in the talk. Now, there's one more thing that I included in Maynard just as a sort of a lark. I called it Perth. Perth is a tiny fourth interpreter written on top of the Python VM using Maynard to assemble some of the low-level stuff that I'm doing in it. It doesn't do very much, but it does define integer, float, and string literals. And it has the following fourth words, which allows you to define your own new functions. That's what colon and semicolon are for. And this is just barely enough for you to be able to write your own Fibonacci because I support recursion. So here's a Fibonacci generator inside of Perth because you really don't have a real programming language until you can run Fibonacci. I don't recommend you use this for anything. But I said I would do it, and here it is. So let's bring everything all together all at once. I'm going to show you a Python virtual machine written in Python itself. Now, I'm not going to run gunk over it because gunk is a really boring function. So instead, I'm going to run, like I said, a Fibonacci generator because you don't have a real VM until you can run Fibonacci. So my VM written in Python is going to run this Python code by examining the bytecodes and taking them apart. It's going to take me 5 slides, so strap in. Def VM function, that's the callable. Star args is the arguments to the function. I define a whole bunch of local variables. Code is the code object. Constants is the const table. Names is the names table. Program is the bytecode. And locals is the number of local variables defined inside the function. Globals dict and built-ins dict, those I need for load globals and store globals theoretically. And I can pull those out of the function itself. You have to pull the built-ins out of the function's own globals dict, by the way. That's important. The instruction pointer I set to 0. I declare a locals array. This is the fast locals array. It's the arguments followed by the number of local variables, and you need to initialize that to some funny uninitialized value. And then the stack, which I'm just using a Python list for, because all I'd ever do is append to the end and pop off the end. While true, I pull out the current instruction at the instruction pointer. I store that in op. I advance by 1. If I have an op-arg, then I disassemble the op-arg from the bytecode stream, pull the op-arg together, and advance the instruction pointer again by 2. The rest of the function is all going to be implementing individual opcodes. So it's all going to be if op double equals something. Op load const, all I do is take the op-arg, look it up in the constants array, push that on the stack. Load fast, same thing, except instead of the constants array, I look in the locals array, and I push it on the stack. Load global, I take the op-arg, I look it up in the names array, that's the name I'm going to look up, and then I try it in the locals dict. If that works, I use that, push it on the stack. Otherwise, I look in the built-ins dict. I don't have a failover. If you use something that isn't defined, then it just falls off the end and nothing happens. Your program crashes. Binary add pops the top 2 things off the stack and pushes the result, having added them together. Subtract, same thing, but with a minus sign. Pop jump if false is going to be our jump instruction. It pops the top thing off the stack, and if that value is false, then the op-arg is going to be the new position of the instruction pointer. We just assign it straight to IP, and we're off to the races. Page 4 of 5. Come on. Oh, sorry, I didn't advance those. I swear someday I will use something besides LibreOffice. Compare op. This is a general purpose instruction that does rich comparisons. So it pops 2 things off the stack, and then op-arg is an integer representing which comparison it wants to do. I had to get those out of the insect module or something. So PyLT means less than operation. LE means less than or equal to operation. I take those, I compute the result, and I push the result on the stack. I forgot I added all of those highlighting stuff. Finally, page 5, call function. The op-arg represents, again, it's a bit field of the number of positional parameters and the keyword-only parameters. The keyword-only parameters are shifted left by 8. So if you have a number greater than 255, then you have keyword-only parameters, which I don't support, so I throw in assert. I pull off the arguments, just stick them right into a list. I pull off the callable object, and then I call the VM recursively, splatting in the arguments, for which it again takes star args at the beginning. The result from VM is going to be the result of the calculation, and so I take that value and just push it on the stack. And finally, return value. I'm asserting that the length of the stack is 1, although Python doesn't actually bother. And I just take the top thing off the stack and return it. And that really is sufficient. Here's a little driver that runs over range 0 through 9. I call print, I call fib, the real one, I call my VM and pass in fib and the number, and I get the same results out. So, in closing, if you try to experiment with bytecode yourself, writing your own functions and writing your own bytecode, expect to see this a whole lot. Python is not particularly resistant to malformed bytecode, and I crashed the Python interpreter a whole lot. And when that happens, you just have to stare at it and think to yourself very quietly what you did wrong. I've talked to other core developers about trying to make it a little bit more resistant. They're like, if you're doing bytecode, you're on your own. Literally, that's what they say. So some resources if you want to follow through on this stuff. You can take a look in the dis, inspect, and future modules. That's where all of the constants that I needed in order to write Maynard were stored, except for one thing that's called the stack effect of the individual opcodes. I had to calculate that myself by pulling it straight out of C. Maynard itself is on Bitbucket and PyPI. If you want to read the C source code for the implementations of the Python bytecodes, that's in ceval.c, which is the biggest file in the Python interpreter because it's the beating heart of Python. And finally, if you want to see a bytecode interpreter written in Python itself, Ned Batchelder has written one called byterun. It's kind of like my last 5 slides, but far more complete, and he actually understands cell variables and free variables. And that's it. I actually do have 3 minutes left for questions, I think. Yes? No? Questions or no?
Yes.
Okay.
Yeah, but I think there is not a keyboard, but I think actually we have 10 more minutes after this.
Oh, we do? My God, I went quicker than ever.
Is there any question? Ready?
Okay.
Yeah, because also I have some. You going to take that? That's funnier.
Hello, thanks a lot for the talk. I think my brain is dripping from my ears.
Mine too.
My question is very simple. Do you have to understand all of that to become a core developer?
No, I didn't understand all of that until I wrote this talk. It's actually, most of the time you spend as a core developer, you spend hacking on extension types. So you'll spend time in the list object or the dict object, and those are using something that's very different. It's using the extension API. There aren't that many people who hack on bytecode, who hack on bytecode generation, who hack on the interpreter part. It really doesn't happen very often. And like I said, I still don't understand free variables or cell variables particularly well. I don't understand closures at all. Uh-oh. Ladies and gentlemen, Andrew Dalkey, who's been doing Python longer than I have.
So what's the reason for a stack machine over a register machine?
A stack machine is simpler. There is currently actually a core developer hacking up Python to see if he can make a register machine. His theory is that the register machine will be faster. He's probably right. But a stack machine is conceptually very simple, and it's also very similar to how machines work in the real world. When you have a C program, it is actually pushing things on the stack and popping them off in order to add them together. The exception to that is when you have specialized registers for doing those things, or you can make it faster by pushing things into registers. But conceptually, old school computers were very much stack machines. Close enough to an answer? Okay.
This might be a little bit stupid because I didn't think about it.
Please.
But is it possible that maximum stack size is unbound for a function?
No. You can compute the maximum possible stack size in advance because you can't have, I don't think Python will allow you to have a loop that adds more stack things every iteration. The stack, every basic block essentially, conceptually, has to have a constant stack change. And in the case of a loop, it would have to be 0. So no, you can absolutely compute the maximum stack value. That said, there are some opcodes that actually the stack effect changes depending on what the op-arg is. So you have to, in order to really compute the stack effect of something, you have to look at all the bytecode, including the op-arg, which makes my assembler very complicated.
Thanks for the talk. In that VM example, you did the globals lookup. So you looked up first in the globals and then in the built-ins.
Yes.
Does it work that way in the real Python interpreter?
Yes. If you had print equals something, in Python 3, print is a function. If you said print equals, or def print, and then you had a print function, your functions in that module would find that print before it found built-in print.
So if you want to make your code faster, it would be a good idea to move it to a local.
Yes, actually, that's a technique that Raymond Hettinger does. If you look in the modules that Raymond has written, collections, I think. I don't think collections is all in Python, but anything that Raymond's written, he will often do that as a speed up, where he will say, def something or other, and then he'll have like len equals len. And that's doing exactly that. It's caching the len object. It's looking it up at the time the function is bound, so it's the time the module is loaded, and it's looking up len and sticking it in the defaults and keeping a reference around to it forever. So if you ever changed len in built-ins, this function that Raymond had written would not notice.
There is something like this in the RE module. There is
RE?
underscore m equals something just to do that quickly.
Yeah. So it does genuinely speed things up because it allows you to skip that globals lookup. There are other core developers who are like, that's such crap. Don't bother. And they get really upset when they see that. But Raymond seems to get away with it.
I was wondering, in the previous slide, one of the first slides, there is unknown, which you said is some shit that some guy forgot during the
Yes.
development. Is there any change between the Python 2 and Python 3 because true and false became keywords? So I was wondering, is there, if instead of none we got something between true or false, there will be any difference? Or
Yes, I think there would be, because true is a different kind of token now. True is a literal token as opposed to being an identifier, and so it would be removed at a different spot in tokenization. So yes, if you disassemble Python 2 code, you would probably see true and false in the names table, even though they would never be referred to. And in Python 3, you wouldn't see those. Okay, I give you all permission to leave.
Thank you.